All right, the last portion of the amines chapter focuses on the preparation and reactions of diazonium salts. And a lot of this will look pretty familiar, so I wanted to do a compare and contrast to something that we saw during our electrophilic aromatic substitution chapter. And if you remember in that chapter, we took nitric acid and we protonated it. And when you protonate nitric acid, using something like H2SO4, what you can end up making is this really strong electrophile. And this electrophile is called the nitronium ion. I think I even misspoke in one of my earlier videos and in the notes and called this the nitrosonium ion, but it is the nitronium ion here, and it's got two oxygens. So in this case, we're using nitric acid. Today what we're going to see is something that's pretty similar, where you can react nitrous acid with acid as well. And when you react this with acid, you get this strong electrophile where the positive charge is shared across the nitrogen and the oxygen. So it's resonance stabilized, and this is called the nitrosonium ion. This is going to be the electrophile that we use today, and this is generally created from nitrous acid. Nitrous acid isn't something we can just buy, so instead we're going to make it primarily from nitrite salts and create it in solution by reacting our nitrite salt with HCl. So let's go ahead and take a look at how we do that. So typically the nitrite salt that's used is sodium nitrite. This is commercially available. And it looks a lot like this, right? So this is going to be sodium nitrite. Normally when you see this written in the book, they just write NaNO2. And you react this with hydrochloric acid. It's the easiest acid to use. You don't need to use sulfuric acid in this case. So we can go ahead, protonate this oxygen, and we can make our nitrous acid. And like I said, this is only created in solution. It's not something you can bottle up as a reagent. And then if you've got excess HCl around, you can do this one more time. And you can protonate this alcohol again. And now we've got a situation where we've got a really good leaving group, right? So in this case, the lone pairs on the oxygen can go ahead and clamp down and kick off this water molecule. And by doing that, we can make our nitrosonium ion. And in this case, I'm going to show the triple bonded form. And we know that this is going to be the major resonance contributor because when we look up here at this form, you see how that nitrogen doesn't have a full octet? That means it's going to be a very, very minor contributor. So in general, I prefer to show this with the triple bond in there. And water is kicked off as the byproduct. So we've gone ahead and we've made our nitrosodium ion. Now what we need to do is see how we can react this with amines. So let's go ahead and draw this. And the reaction's pretty straightforward. So I'm going to kind of condense this down, and I'm just going to say, all right, if we take that sodium nitrite, NaNO2 plus HCl, we're going to have this equilibrium, an equilibrium where very little of our nitrous acid is made, but some of it will get made, and some of that will get converted to our nitrosonium ion. And chloride is going to be our counter anion in this case. If we have an amine around, I'm going to choose a primary amine in this case. The amine lone pair can attack this nitrosonium ion and kick electrons up to that oxygen. And when we do this, we convert that to a double bond. the nitrogen that attacked in still has both of its hydrogens on there, so it's going to have a positive charge. And what we can do next is we can do a proton transfer. So I'm just going to show this as plus minus H+. And what we're going to do is we're going to move one of these protons from the nitrogen over to the oxygen. Let me clean this up a little bit. So this proton was moved over. That means that this oxygen will now have a positive charge. So the question is, what's going to be facilitating this proton transfer? What's deprotonating and then protonating? Well, the water in this case is probably going to do most of that for us. So we will have water around. And in our next step, what we're going to do is we're going to actually have water grab this proton off of the original amine. We're going to clamp down and we're going to kick electrons all the way up to oxygen. Okay, so when we do this, we're going to create a nitrogen-nitrogen double bond. The top nitrogen is going to have this OH group on there, and then we're going to have this R group hanging off right down here. All right, but we're not quite done yet. When we did that, we've created a small amount of acid in solution, so we can go ahead and protonate this top alcohol, make it into a good leaving group, and then eventually shove it off. So let's go ahead and draw this all out. So now this is a good leaving group right here. So the question is, well, how is this going to get shoved off? Well, in this case, we've got lone pairs on these nitrogens. This lone pair can just eject off that water and form a nitrogen-nitrogen triple bond. And it's important to remember that when you do this, that central nitrogen is going to have a positive charge. And when we do this, we have to account for the counter anion, which in this case, we've got chloride around, so this would be our final product. This is called a Diazonium Salt. And these are quite reactive. As you can imagine, the nitrogens already have a triple bond between them. Looks a lot like nitrogen gas that has a triple bond. So these tend to be quite unstable, but they can be used as intermediates during these reactions. They're typically not isolated and stored or transported. All right, so let's take a look at what happens with secondary amines, because the previous example we looked at was with the primary amine. And this one's actually pretty interesting. Again, we're going to take sodium nitrite, NaNO2, and hydrochloric acid. We're going to create a small amount of our nitrosonium ion that looks like this. We're still going to have chloride as our counter anion, but instead of a primary amine, we're just going to use our secondary amine, and I'm just going to make this R2. So just like before, this nitrogen can attack in and kick up electrons to that oxygen. Oops, let me change colors here. We'll get a nitrogen-oxygen double bond. This nitrogen will still have both of its R groups, and it will have this leftover hydrogen, resulting in it having a positive charge. Like I said in the previous one, water can facilitate these proton transfers. So in this case, water is just going to pluck off that proton. And what we're going to get is a neutral intermediate, and it will actually just stop right there. Unlike with primary amines, we can't really do any further reactivities with this. So this would be the final product. These are called N-nitrosamines. All right, it's kind of interesting. These N-nitrosamines have actually been studied a lot in food chemistry and just overall public health. And as far as our understanding goes, we know that they're linked or cause cancer. It's bringing into play a lot of concern with various food products, particularly food products where they're treated with nitrites. So things like bacon, salami, a lot of these cured meats are treated with nitrite. However, it's still kind of debatable if the amount used there is really causing any appreciable harm to the people that consume that meat. But it is something to be aware of when you're buying food at home. These are kind of a little sketchy in the realm of public health. All right. I guess kind of before I go on further, some students will ask, well, okay, why are they putting nitrites in food? It's actually a preservative. And when you think about the amino acids in food, a lot of them have amines dangling off of them. So we're going to form accidental N-nitrosamines that way. But it was a method for preserving food for quite a while. All right, so let's take a look at some other reactions. And the next one I want to look at is with alkyl diazonium salts. And what I mean by alkyl is we're going to be dealing with an alkane, right? So in this case, let's say I've got a primary amine. So this would be the reaction that we did all the way up here, right? So up here we started with a primary amine and we got this final group that had the diazonium portion on it. All right, so we could do the same thing here, but let's take a look at what happens. So if I treat this with NaNO2, sodium nitrite, and HCl, we're going to replace this with a nitrogen-nitrogen triple bond, and we're going to have chloride, right? So this would be referred to as an alkyl diazonium salt. Meaning that diazonium portion is coming off of an alkane, right? All right, the main problem with this, though, is, like I said, this very much wants to form nitrogen gas. So this will spontaneously decompose, forming a carbocation that will rearrange and do a bunch of unwanted chemistry. So this is super unstable / potentially explosive. So really, it's not the most ideal chemistry for somebody to do. You don't generally want to make something that's really unstable and could explode on you. So as far as we're concerned, this is not a synthetically useful reaction. So the question is, well, when would we make these diazonium salts then with primary amines? Well, we just have to be careful not to use alkanes. We can use aromatic molecules. These are called Aryl diazonium salts. All right, and Aryl just means that there's some sort of aromatic ring involved here. So what I mean by that is if we start with aniline, what we can do is treat it with sodium nitrite and HCl, and we can make this diazonium salt, but now instead of an alkane, we've got an aromatic ring. This provides some level of stability, right? So this is going to be our Aryl diazonium salt. All right, and the cool thing with this is this intermediate is hugely versatile. All right, so let's take a look at what we can do with it. Well, there's a series of reactions called Mire reactions, where we can functionalize these in a variety of different ways. There's 4 main pathways for the Mire reaction. One is we can treat it with copper chloride, specifically copper 1 chloride, and we can just swap off that diazonium salt for a chlorine. So this can be pretty useful, especially if you're in a situation where you can't really do the halogenation as readily. Or you can do the same thing with copper bromide. Let me slide this up a little bit so that we have enough room. And you can get a bromine installed. Or you can do this with copper iodide. This is a reaction that we couldn't really do with electrophilic aromatic substitution. And we can get an iodine installed, no problem. And then the last one that's kind of neat is we can react it with copper cyanide. And as you can imagine, we can get a nitrile installed this way. These are all referred to as the Mire reactions. And it's a pretty useful tool for functionalizing aromatic molecules, especially if you've got an aniline to begin with. All right, so there are a few offshoots, meaning similar reactions. So let's write those down. So variations. All right, the first one's kind of neat. If we have a diazonium salt, and we usually make these from anilines, we can just treat this with water and crank up the heat a little bit. And when we do this, we can actually swap off that diazonium salt for an alcohol. And so you might be thinking, well, in that chapter where we talked about reactions of aromatic molecules, we said that we can make phenols by using nucleophilic aromatic substitution. But in this case, it's a lot more gentle. And let me explain why. So it's a good alternative to nucleophilic aromatic substitution and elimination addition. All right, so in this case, it's better than nucleophilic aromatic substitution because we don't need strong electron withdrawing groups. So in this case, you can see we didn't have nitro groups in the ortho para position, but this worked just fine. Right? And then for elimination addition, one thing I said was that it required ridiculously high temperatures to get phenols. So this one doesn't require crazy temps. So this is a much easier way to make a lot of these phenols. All right, so that's one variation that's really useful. The other one that's kind of useful is if you have a diazonium salt, you can actually just remove it and replace it with a hydrogen. So let's say we've got this molecule, and we just want to get rid of that nitrogen group. And we just want to go back to our regular aromatic molecule. Well, to do that, what we can do is treat this with H3PO2. This is hypophosphorous acid. It's not phosphoric acid, it's a different type of acid, and we're actually able to just go straight back. So if you have an NH2 group that you maybe were using as an ortho-para director, but in the end you want to remove it from your molecule, one trick is to turn it into a diazonium salt and then just remove it with hypophosphorous acid. So it's kind of a neat workaround. All right. Now, the last one I want to talk about is the azo coupling reaction. And this one is actually related directly to the lab experiment that we do in Chem 263. And that is, if you have a starting material that's an aniline, you can treat it with your nitrosonium ion, right? So let's just go ahead and show the full reaction. So in this case, we've got our nitrosonium ion, and if you remember, this right here can be made by mixing HCl plus NaNO2. And when we do this reaction, the nitrogen is going to attack in, kick electrons over to the oxygen. we're going to get this intermediate where this nitrogen has a positive charge. And then we're going to move that extra proton, meaning the one coming off the nitrogen right here, over to the oxygen. So I'll just write plus minus H plus. And then if we have water floating around, the water can help us out. And let's actually show this bond here. And the water is going to grab this hydrogen, clamp down, and push electrons all the way to oxygen. Oops, let me clean up my nitrogen here. There we go. And then next up, we're going to protonate our alcohol. Make it into a good leaving group. So just kind of reiterating the chemistry we've done before. Like I said, this is now a leaving group. So in our next step, we can clamp down and kick off our leaving group. All right, so we've made our Aryl Diazonium Salt, this highly reactive species, and we've got chloride as our counter anion. All right, what we can do next is we can have this react with some sort of nucleophile, right? Because this right here is going to be an electrophile. It's got a positive charge. So we can actually use an aromatic ring as a nucleophile, and I'm going to make this purple. And we know that aromatic rings aren't super good nucleophiles, so it works best if you have an electron donating group coming off of this. So I'm going to write that as EDG. And so this is going to be our nucleophile. Let me fix this. So this is going to be our nucleophile. And this is going to be our electrophile. And if we've got an electron donating group here, that means that our ortho and para positions are going to be most reactive, right? Those are going to be the nucleophilic sites. In this case, the para position is usually more sterically accessible. So this can attack in and kick electrons up to the nitrogen. All right, so this looks a lot like the electrophilic aromatic substitution chemistry that we saw really early on in this term. And when we do this, we're changing this to a carbon-nitrogen double bond. And then this other ring is going to briefly lose its aromaticity. We're going to have a positive charge right here. And we're going to make this sigma complex, right? And we still have our water floating around. And this water can help grab this proton and restore aromaticity. And these are found in a lot of commercial products. These these Azo Dyes. They're used in a variety of food colorings and commercial dyes. People just traditionally call these Azo Dyes. There's a huge variety of them. But the idea behind these, though, is that they're highly colorful due to extended conjugation. We've linked the conjugation of one aromatic molecule all the way to the other, and because there's a nitrogen-nitrogen double bond, we've bridged the gap between the two. So in our lab video, you'll be able to see the colorful Azo dye that I made that was a almost bright orange like you'd see on a traffic cone, and we were able to make that from 2 colorless, or white powders, I should say. All right, last but not least, before we finish up the chapter, I did want to point out that at the end of our textbook, for every chapter, there's a study guide kind of listing the reactions we should know for the chapters. So this is an excellent way to review. It goes over all of the sand-Mire reactions, all of the new ones that we've covered. This is another one that I didn't talk about in this video, but you can treat a diazonium salt with HBF4 and get a fluorine on there. There's a lot of other chemistry we can do too, but if you want to use this as a study guide, feel free to pull up this fill in the blank, print it out, and just try to remember what reagents you would need for every conversion. All right, good luck studying.